Okay, so with the help of De Mor's theorem that we discussed so far, how can we find out the n roots, like 2 cube roots or 2 square roots, 3 cube roots and 4 fourth roots of some number. So let us discuss that thing. How can we find out nth roots of, let's say, a complex number z. So the first thing is that we can write z as this, or cos theta plus I sin theta, and what we are interested in, z raised to 1 over n, because we are going to find out the nth roots of z, and how many are these in total? These will be nth roots of a complex number z. So this can be defined by some values, let's say wk, where k runs from 0, 1, 2 up to n minus 1. If we are starting from 0, we'll end at n minus 1, and these values in total become n. So it is simply, we have this complex number, and what we are doing, we are raising this complex number to power 1 over n. So what happens basically, this 1 over n is raised to r, so this becomes wk r power 1 over n, and then cos theta plus I sin theta. What we do basically, we multiply this angle with 1 over n by using De Mor's theorem. Multiplying 1 over n means dividing by n. And one extra thing that we can do is we can add 2k pi here. And the question is why? Period. Yes. It is because of the argument of this complex number. Because the argument of this complex number is not cos theta, it's going to be cos theta plus 2k pi. Because the period of cos is going to be 2k pi, and where k is the integer starting from 0 to all the values, but I am going to stop it to n minus 1. What's the reason?
0.
This is the period, we know very well. 2k pi is period. What is k? K is any integer. But I started k from 0, and I am going to end it at n minus 1. Why I am not going to other values like n or n plus 1 or n plus 2 and so on? Yes, but why not extra? Because it says according to the formula you can go ahead. But the problem is when you go ahead, when you write n, you will get the same root as 0. So it will be the repetition. It will be the repetition. So you can go ahead with all the integers, but you will exactly get n unique roots, and other roots will be repeated. So we are not interested in repeated roots. That's the problem. Yes. Okay, so let us go ahead to see an example. We have this number, it's a complex number 1 or 1 plus ei, and we are interested in this one. So what would be answer? It would be wk, which is, let me write the formula, or you can find out what is r and what is theta. What is r in this case? 1. What is theta? 0, because we are exactly on x-axis. We have this complex number which lies here. So what is the angle? The angle is 0. So I am going to write everything in this formula. What is r? 1 1 over 3 cos, what is theta? theta is 0, so I am writing simply 2k pi over n. But what is n? 3 plus I sine 2k pi over 3. And what is the value of k? 0, 1, 2. 0, 1, 2. Because if I am going after that, I will be getting exactly the same value. So what is W0? So you write exactly 0 here. Cos 0 is 1, sin 0 is 0. So that's going to be 1. So 1 cube root of 1 is going to be 1. What is the other? W1. So I put 1 here. Cos 2 pi over 3. What is that? Cos 2 pi over 3. What is 2 pi over 3? 120. 120 means in the second quadrant. So it becomes, okay, whatever, let me write this. Cos 2 pi over 3 plus I sine 2 pi over 3. Ink filthy? Ink fill कितने देगा? So what is W2? So it is cos 4 pi over 3 plus I sine 4 pi over 3. So this is what we get. 3 cube roots of 1. Okay, and the good thing about these is 1 lies here, 1 cube root. The another lies at the angle of 120. So basically, if we draw a circle whose radius is exactly the mod of this complex number, means this one, then your all the roots will lie on this circle, means one root here, other root here, and other root here. And if you join these roots, you will exactly get a regular n-gon. In this case, it is a regular triangle. Otherwise, it will be a regular n-gon. Like if there are 4 roots, it will be in a square. If there are 5 roots, it's a regular pentagon and regular hexagon and so on. And it is always, it's not only this case, it is always there. Okay, any question? So let us write some equations of some shapes, geometric shapes, in the form of complex numbers and their modulus. So let us say we have a circle with a radius r and let's say center. Z naught can be written as z minus z naught equals r. So whenever we find this equation, it is an equation of a circle with center z naught and the radius is going to be r. And one thing, it's a circle, so it's a shape like this. With, let's say, center is origin, we call it z naught, and the radius is going to be r. We have something what we call open disk, and we have what we call closed disk as well. So it is simply this thing. So it means all the complex numbers z which satisfy this property are to be the part of open disk. And a circle is basically a boundary.
Yes, sir.
We call it a one-dimensional manifold. And what is a disk? Open disk. You don't have boundary, but all the points which are inside this boundary. And closed disk means this particular thing. So these are all the points on the boundary as well as inside. So this is what we call a two-dimensional manifold, and this one is one-dimensional, not two-dimensional. And one thing else, so there is a difference between what is a disk and what is a circle, and here it is clear. Why we are going to discuss these things? Because we will be using these later on. So what is a punctured disk? So it is z minus z naught is less than r, but it is going to be greater than 0. It means I have a disk with radius exactly r and all the points which are less than r, but I am going to exclude 0 out of it. So I have all these points, but 0 is not there. And we call it's a disk, but it should be open disk, so I am going to say that okay, the boundary is this, because this is open disk. So this is open disk, but since 0 is not included, so we call it a punctured disk.
0 fixed will be good cost.
Yes, there can be, but for some purposes, okay, we are saying that the center is not included, for example. Then I can write this as z naught as well. And then there is some another thing, what we call annulus. And here the example is a circular annulus. So I have some R1 which is less than R2, and z minus z naught is less than R2 but greater than R1. And it's basically a shape like this. I have a bigger circle whose radius is R2. It means this value is exactly R2. And I have a smaller circle whose radius is exactly R1. And this is a set of all the points which are in between these circles.
Tube.
Yes, it's a tube. What we call it annulus. But circular annulus. But since these are open, so I should rather mention a dotted line here. These things will be helpful a lot when we study Taylor series or Lorentz series. Basically in Lorentz series, we have this particular idea of annulus.
He says that okay, circle is also two manifold.
No, it's one dimensional,
One dimension.
not two. Because circle is just the points on this line,
Onto that.
but the disk is everything inside.
जेको असां एलिमेंट्री लेवल ते स्कूल में पढ़ंदा एरिया त मालूम कंदा सर्किल जी न अगर एरिया 2D में सेट करते हैं या जुगाड़ दे के सर
सर्कुलर रीजन असां कंसीडर कंदा आहियूं ऐं असां चवंदा आहियूं ठीकु आहे अहिड़ो रीजन आहे जेको बाउंडेड आहे हिकिड़े सर्किल सां.
तो सर्कल प्लस ठीक है पर एरिया अच्छे से ने उन से
असां कंदा आहियूं एरिया सर्कुलर रीजन जी,
सर्कुलर रीजन
सर्किल जी एरिया न कंदा आहियूं. असां चवंदा आहियूं द एरिया ऑफ दिस rectangular region, the circular region. So we are basically, we have an area and we are going to enclose it into a circle.
ये है फॉर्म की है तो एरिया ये एरिया है ना सॼो.
Yes, it's area, it's area.
हां त पोइ असां हुन खे असां पोइ बि जॾहिं एरिया माउंट कयूं था त पोइ बि इहो 2D न थियणु खपे 1D
आहे माना सर्किल 1D आहे. बेसिक लेवल ते असां चवंदा ठीकु आहे एडी एरिया आहे जेका enclosed आहे
इन अंदर अची सघे.
बिल्कुलु बिल्कुलु असां उहे चवंदा आहियूं उहो कॉन्सेप्ट यूज़ कंदा आहियूं.
Salah. Krishna. Can you
Okay, so complex exponential exponential is e raised to z, which is simply e raised to x plus iy, and we can write this into this form, and by using Euler's theorem this becomes cos y plus I sin y. And one thing that we can notice from here is the modulus of this exponential function is always going to be this e raised to x, because when you apply modulus on this one, this becomes cos square plus sin square, which is equal to 1, and we are only left with this particular condition. No, because the modulus of this quantity a plus bi
always positive, see.
is this thing.
Say yes, see.
Because we ignore the I, we only take the imaginary part. And what is the argument of this one? What is the argument? Argument of exponential function is always y. Is always y. Because argument is basically this angle. This is or cos theta plus iota sin theta. So theta is y. That's the argument.
Y component is move कर दो तो एक ही खड़ी है.
Yes. When you move it y, it becomes an angle. And we can also define a period. So we got 2 and y, where n is in the set of integers. And you have e raised to z, to take its conjugate, it is same as e raised to z conjugate. And there are some other obvious properties, but I am not going to write. And one thing is that e power z is periodic with period. What is the period of e power z? Period is always 2 pi, because if you take f of z to be e raised to z, if you take f of z plus 2 pi I, which is e raised to z plus 2 pi I, these will always be. Just you expand and you will get the same thing. If you don't expand, you just write this thing in this way. E power z times e power 2 pi I, and this thing is always equal to 1. This thing is always equal to 1, because you know very well we can write this thing as cos 2 pi plus I sin 2 pi, which is equal to 1. So the period of an exponential function is 2 pi r. We can deduce so many other things out of this, and let us take a few. You can deduce that sin z is e raised to iz minus e raised to minus iz divided by 2y, and cosine z is same as this, but a few changes are there, divided by 2. We can simply deduce these two things with the help of Euler's theorem. And what is Euler's theorem? It is this: e power iz is cos z plus I sin z. This is what we call Euler's theorem. And by definition, we know that is by definition. What is sin hyperbolic z and cos hyperbolic z? Where do these things come from? These things come from Euler's theorem. Okay. And what is the definition of these things? things are not coming out of some other relation, but these are defined in some way. That sine hyperbolic z is defined as e power z minus e power minus z divided by 2, and this is defined as this. This is by definition, and these are the results which are coming out of this. Can we relate these things? Can we relate sine z and sine hyperbolic z? One thing is that what is sine iz? What do I need to do? Just replace z with iz. That becomes iz minus 2r. So this becomes now e power minus e power z divided by 2r, and when this I goes in denominator it becomes minus I. So I am not writing minus, and I am applying that minus over here. This becomes e power z minus e power minus z. This becomes sine hyperbolic z. So sine I z same as I times sine hyperbolic z, and cos I z is same as cos hyperbolic z. There is no I here. We can reduce this relation as well. Okay, one thing else. Can you tell me what are the real and imaginary parts of sine z? Sine x plus iy, and I think we can write it sine alpha cos theta plus cos alpha sine theta. We know very well this relation. And now cos iy is same as cos hyperbolic y, and sine iy is same as I times sine hyperbolic y, and this thing remains same. Okay, so sine z, what is the real part? Is this one, and what is the imaginary part? Is this one. Imaginary part of sine z. Now, similarly, you can find out what is the real and imaginary part of cosine and so on. Can you tell me what is this? It's a bit easy. One. This is not bounded. Sine x and real is bounded between 0 and 1. But this is not bounded. Complex sinusoidal functions are not bounded. Okay, so let us do this. Real part squared, sine square x, cos square hyperbolic y, cos square x, sine square. Can we do something now? If we can do something, then we are okay, otherwise this is going to be the answer. But we can do something. The final answer that I cannot think of right now, but is this one. Square root of sine square x plus sine hyperbolic square 1. This is going to be the mod of sine z. The question is how can we get this? No. We can deduce something out of this by writing cos hyperbolic in the terms of sine hyperbolic, or sine hyperbolic in terms of cos hyperbolic. What is the relation between cos hyperbolic and sine hyperbolic?
We should use the
Yes, these will be, but there is a relation. theta plus cos square theta. Always 1. And what is this? Hyperbolic square theta. Not this. If we know this relationship, then we can do this easily. Otherwise, I think this quantity is equal to sine hyperbolic square by this. I think. I'm not sure. But if we put this thing is equal to this one, then sine square x sine hyperbolic square y cos square x sine hyperbolic square y. Sine hyperbolic square goes common, which is this. And in bracket we get sine square plus cos square, which is 1. Removed sine square x multiplied by 1 is sine square. So if we replace this with this, then we are done.
It was a minus 1 or something.
Is equal to 1. It means it is this. Cos hyperbolic minus sine hyperbolic. The identity is this one. So if we are going to use that one over here, we are exactly getting what is the mod of sine z. And similarly, we can separate the real and imaginary parts of cosine and sine hyperbolic, cosine hyperbolic as well. I got this question in test as well. So, what is the mod of sine z? That's very simple, but we need to do something, then we are getting the answer exactly. So we know very well sine, cosine, cosec, sec and period 2 pi. In the period of 10, cot is pi. And one thing is that is a bit important, that real and complex sine and cosine are not real and complex, but real sine and cosine are bounded functions. We know very well sine of x is bounded by 1, and I have taken absolute value, so it will always be greater than 0. Similarly cosine, but complex sine and cosine are not bounded. Can you tell me why? This is sine z. It's sine of a complex number. It is bounded means when you take its absolute value, it should be less than or equal to something. I am taking its absolute value, the answer is this. What is the problem in this one? The sine x is bounded, but these hyperbolic functions are not bounded. Because hyperbolic functions involve exponentials, and exponentials grow, you know very well. So this is unbounded.